What is this?
It's some kid.
It's
a person using a camera angle.
He thinks he's tall.
It's full
Yeah,
middle
now-
ground and background.
There might even be a little bit of Photoshop here because this looks pretty darn good. But what is this? It's the Leaning Tower of Pisa. Right? So why do we care about the Leaning Tower of Pisa? Well, it might fall over. Yeah, that got Athena's attention, but not really anybody else. It might fall over.
On him.
No, not probably on him, at least based off that perspective. Seriously, if the angle of elevation ever falls below 83 degrees, engineers have determined, like, it's going down. So the question is, where is it now? How safe is it? Right? So
And when it will fall over.
engineers do closely monitor the tower, like it is constantly being monitored. And when we take some measurements here, to get out to exactly below the edge of the tower, like if you went on top of the tower and dropped an object, that would be 5 meters out from where the tower actually touches the ground. And the tower, we know, is actually 50 feet vertically up. So if they drop the tape measure, or not 50 feet, sorry, 50 meters, it's about 150 feet, right? Close. 50 meters, 5 meters. How are we able to use that to determine the angle? It's so weird to see Mrs. Golden walk by. To determine the angle at which the tower is at. Well, this gets us into a branch called trigonometry.
Wow.
So we're doing a little bit of trigonometry, you know.
So we know it's less than 90.
Yeah.
What?
Less than 90, but it's more than.
It's more than 83
Or else it'd be down.
Yeah. So it must
What
be
triangle could we know the angle of elevation just based off leg lengths? Just a person.
Oh, isn't it like if it's an isosceles?
Ooh. What about isosceles?
Angles are the same.
No.
So,
Yeah.
yeah, 2 of the angles are the same, so then that's easier if you know one to figure out. Yeah. Because if the 2 angles are the same, then you know what the other angle is.
Then that one has to be 90.
So if we had a triangle like 5 and 5,
Then you know what the other angle is.
yeah, we know it's a 45-degree angle of elevation. Right? So the triangle that we are looking at with the Tower of Pisa, right, here's our tower. These angles are unknown, but what we have right now is 5 and 50.
Okay.
4.5.
Now what about, wait, what? So obviously mine's not drawn accurately necessarily. My 50 is definitely not 10 times my 5. But that's okay because I want to be able to work with this. Are there any other special triangles? Cough, special. Considering that's part of the name of these triangles that I'm referencing. There's another word involved there. Special right triangles? Do we not remember special right triangles? Did we not learn about them in Math 8 and Math 9?
Paul was really
You
good at
like,
teaching
I
us.
might have, but I'm not 100% sure.
I don't even remember during
Oh,
this
yeah.
It's been a while.
So maybe you haven't learned them yet, but this is a special right triangle because it has 2 side lengths the same. Now the other special right triangle is the 30, 60, 90. So if you don't know about this yet, it's okay, and we'll come back to it because I'm again over teaching. But special right triangles are the 2 types of right triangles where if we know that they have these angle relationships, we know they have specific side relationships. So here's the cool relationship that happens here. The short leg is always opposite the 30 degrees. The hypotenuse will be double the short leg, always, in a 30, 60, 90. And then the long leg is radical 3 times the short leg.
Out, because we know the two legs, then we should find out the hypotenuse and then see if it fits that. See if it's a special triangle.
Yeah. So, over the next few days, we're going to be doing stuff like this, and we're going to have a few different resource pages that work with this, but you have this in front of you, right? An 11-degree angle of elevation when we're working with a slope of 1/5, right? So, go ahead and notate that, kind of like formalize that, like write it down on your own. Well, so that would also, we could like extend that. We could have any manipulation of that slope, right? So we wouldn't just be stuck using 1/5. Make some dilated triangles on your paper to go ahead and make more. I mean, or you can obviously write out like a proportion using that slope. So if we go out here, we can also work with 2 and 10.
Yeah.
Or 3 and 15. Or 4 and 20. Or 5 25ths. Okay, that's fine. We have 5 25ths. So that's rise, run. So what would we, like, what if I start playing with this a little bit, and I instead put a point here to connect down? Yeah, the angle's going to get bigger. We need to try to formalize, like, a rule for how this is going to work. What about, like, there?
Oh, it's the angle, this angle times 3.
Would it be there? That's what I'm asking, right? Like, that's the question I'm asking.
Well, the angle is increased.
No, because the point, like, where the 1 and the 5 is, like, times 3. Now it's times 4. That makes, wait, get it all the way up to 90. Let's see how big it is then. If it's more than 90, then I feel like those lines are good.
They probably are. What's this now?
It's a special triangle.
What's the height?
5.
And the
So
length
then
is
it's
5.
It's not special yet.
so then it's the isosceles.
Ooh. Which, wait, we said isosceles has what angle measure? 45.
Oh wait.
Not 55.
Get
Right.
math calculator.
Right, so the temptation, Liang said, was, yeah, when I go up, when I make my slope 2/5, it doubles my angle, right? I'd have 22 instead, but, well, maybe not quite, actually. Right, so it's not that easy. We can't just say, like, oh, if my slope is 3/5, it's 33. That's not quite true. Does that make sense why we can't just double? Because we just proved the times 5 doesn't work. Interesting.
Times 9.
So, Tara does think she sees a pattern, though. Tara's actually a friend of mine, Scott and Tara. They have a cute kid. So, she asked, what if I draw a slope triangle on this line with a y of 6? Right? I don't think we got to a y of 6. What would her x be? Or what if, like, x is 40? What would y be? So figure out those two questions. If y was 6, what would x be? And if x was 40, two different questions, right? Because we have this. So remember, these are rise over run ratios. Oh, yeah. It gets really hot in the 7th grade. I mean, they were just in here for an hour and a half straight. Because I taught Mr. Smith's class. So remember, this is delta y over delta x. Right? Rise over run. So what Tara's asking is, what if the delta y is 6? One that we can't quite get to, right? Because this is not yet 6. So she starts to speculate. Like, what if it was?
It looks like the pattern is that it's increasing by 5.
It'd be over 30, right? Because the denominators keep increasing by 5. Or then Scott, let's say, because I forget who they actually named in the problem, said, well, what if actually delta x is 40? Like, we can't go that far. Yeah. This would be 8. So all of these ratios, we know, would create an angle of 11. But that's only helpful if we want the angle of 11. Right? What if we're not working with 11? Or what if we're not working with a slope that is 1/5? Right? This is where, how is this useful is really what we're saying. So you helped out Tara. Great, wonderful. We found those values. But why? What does it matter? So on your resource page, so right here, part A, bottom of your front resource page. We want to try this with the line y equals 2/5 x. Now you have a protractor. What if we try to measure our angle and see how big it is? So try that out. Draw out a slope triangle of 2/5 x. Yep, on your resource page. And then we're going to measure with a protractor. It's just mad. 2/5, right? I mean, rise of 2, run of. So then I ended up really doing like 4/10 also. Anyone not have a protractor? We can still actually use this program. We just have to use it the right way. So make sure you flip your protractor so you can read it.
Yeah, it looks like I got 22.
Yeah. That makes sense because it's times 2 of the 11, which was from 1/5.
Man, it does, right? It looks like it'd be. Well, let's try the 3/5, right? That looks really close to 30, doesn't it? Maybe just over.
So what if, flip your paper to the back. You have the line PQ. Set your protractor 0 on PQ. I don't think I gave myself one of these. Make an angle of 18 degrees. Make an angle of 18 degrees. And then try to find where it lines up. So try to find the slope ratio of 18 degrees. Ooh, this looks pretty close. This looks really close. So if we forced this to be 18 degrees, what's your slope seem to come out to be?
It seems like 130.
Yeah,
Oh, by the way,
2.6.
You realize I think there's another paper if you want.
Hmm?
I'm pretty sure there's another paper.
Is there? I couldn't remember if I only made 5 or if I made myself one too. I try to conserve paper when I can. So all right, so hypothetically, a slope of 1/3 is 18 degrees. Yeah? Okay. Trying to figure out what we can do with that. Now, this is one of those I'm going to try to make your life easier. Think about this for a moment. The line y equals x plus 4. If we go to graph that, now you can if you want to. What do we know? Like, tell me the info we know just by reading the xy. X is always 4 greater than y. Somebody said slope.
Yeah, the
Slope
slope is 1.
is 1. So a slope ratio of 1 to 1 or 5 to 5 or whatever. And what do we say that degrees would be? 45. Right, so now we're starting to derive a 1 to 3 is 18 degrees. A 1 to 1 is 45 degrees. We should really kind of start to document these. I may run and make you guys copies really fast. We're not supposed to have this resource page till like tomorrow. So I do want to give it to you though because I think you'd rather appreciate it now. While I'm making you copies really fast, test these out.
On your note paper?
Or on the graph, the graph that's left. Since we just talked about this, we would know that slope without even having to graph it. It's 45 degrees. A 1 to 1, a slope of 1 is 45 degrees because it makes an isosceles triangle. So test out your 71. I'll be right back. I printed it but decided I wasn't going to copy it, and I should have decided just to copy it today. I can't just print 5 because they're 2 different sheets, and I want to give you the answer key.
All slope triangles.
No.
No, because they can have different ratios.
So do we write down both?
Yeah, where are we writing this down?
Whatever. If the slope ratio is 1 to
These are notes,
and the
so you
slope
don't write-
angle is approximately
didn't go on my notes because my notes.
Oh yeah, that makes sense.
My notes are. I didn't like going through them.
I haven't done anything.
Why you sleeping my notebook?
A complete waste of graphic.
It's approximately 11 degrees. You just have to go back to it. We did. Yes. And it's wait.
Books can be different.
Okay, wait. Slope.
Yes. We did the exact same thing. But wait, what if it's different though?
It can.
I guess that's yes.
So if the
Right.
slope ratio is 1/5, then the slope
Different
angle
lines
is
have
that's
different
true.
slope
Yeah.
angles
Yeah, that
and
makes
different
sense.
slope
I mean, what else would you
ratios.
do?
I wonder.
Yes. Angle can't be different. Angle won't change.
Did you break the pollution?
No, it was already broken.
The
There's
line?
no nice
Yeah, I guess.
distance there.
Because that makes sense.
Yeah, lines will
Yeah.
have different slope angles with yeah.
Yes.
Yes, I'm just gonna write yes, I'm done with this. Wait, hold up. What did you guys say? Y equals x plus 4, so the ratio is what? 1.
One.
So you said the slope was 1.
Yeah.
Sorry, that's
Okay, well,
Trigonometry.
I'm gonna put this in here.
45 degrees.
I kind of just
What?
wanna.
What if it's like if x, but that's not the slope.
Wait.
Is it? Like y equals x plus 4. How?
Yeah, so. Because it's x, it's just x, so x is.
Say x
So
was,
1x basically. So it's
if
1x
x was 1.
So
Say
then
x
y
was
would
1,
be
then y
5.
would be 5. And it increases like this, but that is not 1. 1, 1, 1. Like,
Okay, so
like
Just a y, just a normal equation. Just y.
should I just
Equals
move the
y
board
equals
so we
x
can
plus
start
4 is
working on
slope
homework?
of 1 and
Or that
x
Oh.
equals
Alright, you have to promise me something.
okay.
I wanted to make these copies the most efficient way possible. How CPM does this is they give you a one-sided sheet that is mainly not filled in, and then 2 days from now we give you a one-sided sheet filled in. I made it two-sided, but I would request that you don't look at the back yet.
Okay.
Okay, which now I know the only thing you want to do is
So
look
I
at the
shouldn't
back.
go flip it over?
Don't pay attention to the back.
So what we just found out, we have all of those things on here. Right, that 18 degrees, go down to where we said 18 degrees. What did we say that slope triangle was?
1/3.
1/3. So draw it out, like do a little sketch of what a 1 to 3 triangle would kind of look like. And you could use your ruler if you want. Do like 1 centimeter tall, 3 centimeters wide. Right here, on the front, 18 degrees.
It does have centimeters. Wow.
What else did we find? Did we talk about? Look down the left side. Didn't we kind of see 22? Although we were worried that our hypothesis might not be correct, didn't 22 look like it was 2/5? Or didn't the slope triangle of 2/5 that we set up look like 22? So I think we should know that one also, right? So yeah, go down to 22. That slope triangle was a 2 to 5.
Wait, go down to 22.
22 degrees. Yeah, we said that was 2 to 5. Because remember the 1 to 5, we doubled it, and it did look like 2 to 5.
I'm not doing this one.
Now, keep looking down the left side. 45 degrees, we figured out that one too. Any number over itself. Right? So you could just do like z over z, or you could draw a 5 over 5. Or like 5 compared to 5, sorry, rise, run of 5. Remember, it's any isosceles. Any z over z ratio. We said 18 degrees.
45 is 1, right?
So 1/1.
We said this was 2
Wait.
to 5.
1/1 equals 1.
This is 1/3, 2/5. Anything over itself.
Oh.
22 is 2/5.
5 over 5.
Now 55. We figured out that.
Yeah.
Or no, we didn't.
But
We thought we figured it out.
it's a little iffy.
We looked at 5 over 5, and it wasn't 55, right? We thought it would be. Because compared to the 1 over 5, we thought, well, yeah, we just keep multiplying because it worked for 2/5. It didn't work for this, though, right? We've got a good amount of time left. We got a good 10 minutes left. I want you guys to split up these angles and see if we can figure out what approximate slope ratio matches. So, like, call dibs on angles, right, and just try it on your graph paper or whatever else you want. So, like, 0 degrees, we should be able to fill that in on our own.
45 degrees.
Wait, what were we put for 0 there?
0 degrees is 0 over anything, right? So that slope triangle is flat line. That's really sad. So somebody needs to do 8 degrees. Who would do that? Okay, so if you guys got 8 degrees, 55 goes to Liang. Who wants 68? 70? Sammy then?
I guess I'll do 70.
All right, let's dive in. See if we can figure out what these approximate ratios would
Hey,
be.
Tina, you want to get one too?
No.
I will tell you, 2 of those are going to be rather difficult.
I hope it isn't
Well,
mine,
you
but
tell
I
me
bet
which
it is.
one.
It's probably 9. 55 is not a normal number.
So I got 70.
55 shouldn't be that terrible.
Yes.
What about 70?
Some haha people, I could just be lying to you.
Ha ha.
Oh, wait, hold on.
He wouldn't do that.
Oh, wouldn't I?
Yes, he would.
You're like, he wouldn't do that.
Lies.
Unless we were learning something important.
Oh,
You're learning trigonometry.
Oh boy.
Nah, it's fine.
So when my mom asked what I did today, should I just say
I'm too loud to
trigonometry?
find my touch her.
Yeah, I mean, that is the answer to what did we do today. It is trigonometry.
Sometimes I ask her because I'm a little confused, and she's like, "Do you think I know what you're doing?"
I'm going to use the little squares just because we don't know how funky what we're working with is.
Mine is 3/4. 55 is 3/4. There you go.
3/4. 55 should be over a 1-to-1 ratio.
No, oh wait.
Okay.
I mean,
Right.
what? Where's
Wait.
No. Wait, hold on. Hold up. Like, hold up.
Wait a minute, put a little love in it.
Stop it,
No.
stop it, stop it, stop it.
Hold up.
I think mine's the hard one because I'm very confused.
Wait.
I'm going to try 55 because Liang seems like he's having a time.
Is it 4?
Is it like 4.5 over 4?
It's rise over rise. So how do I? Oh, it's 4/3. I'm done.
55.
Never mind. I'm
Wait,
actually.
what?
Are you sure about that?
Yep, I am.
Because you sounded really iffy to start.
Because I was doing run over rise instead of rise over run.
That'll get you.
I got 180. You might want to try mine because I'm a little very, very confused. Wait, Sammy, what one are you doing? 70. 70?
I know, Liang, you said yours is what? 5 over 4?
No, 4 over 3.
4 over 3. I mean, it's a little bit over 4, though.
Mine wasn't.
Well, then yours is wrong. No, I mean, but seriously, if we're trying to be accurate, I could almost say 3/2, but it's not quite there. I could almost say 4/3, but it's not quite there. Hold on. We're on this one right now. So, sorry, I'm trying to hold my camera because this is really difficult. If we look for the best intersection point here, the best, not really great, not really, no,
Wait, which one
no,
did you do?
no, this is 55 degrees. No. This is pretty good.
It's close, but not quite. I don't think that's what it is.
That's not terrible. It's,
I don't think that's what it is.
so yeah, if we use this point, 7/5 is not bad.
It might be 5/2, but it's like approximately 5/2.
So right here, this point, that is actually what CPM is referencing as the first best lined up point. Because again, we're humans and we're trying to draw. 55 degrees has a good point at 10/7 approximately. 10/7. 70 degrees, it's ugly as all get out.
I said like 5/2-ish.
Actually, that's pretty close.
It's like
They
close,
use
but not quite
13.737/5. It's not a nice one.
So mine was the one that was
Have everyone do 84. Now, if we didn't want to do 84,
wait, what's for 8 and 68?
we'll come back to those. If we didn't want to do 84 right here, what else could we do instead?
We could do wait 6, because if you do like a 90-degree angle.
Not. Ooh, yeah, 6. But why? They are.
Because 84 plus 6 equals 90.
Yeah, they're complementary. So I'll get the inverse, right? If I do 6 instead of
I
84,
feel like no one else is listening, but
I know. Now I'm changing my XY just because I want to cheat here. So I'm going to do 6 degrees. Now you could do 84, but it's really, really steep. I'm going to do 6. By the way, use your ticks way out here, even if you're not using the 180. If you look at the screen, this is 6 degrees in this situation, right? That tick out there. Wait a minute. That's on a dot. The tick I just put for 6 degrees.
Wow, you don't even have to draw a line.
Oh my gosh. This is 110. Or the other way around would be 10/1. So where you have 84
so 84
degrees,
is 10/1?
84 degrees is 10/1. Ah, way too zoomed in. Now wait a minute. 10/1 relates back to something we talked about today. The Tower of Pisa. Because if we circle back, see how this all comes back together.
All comes together.
Its slope is a ratio of
So
10
the
to
degree
1.
is 84 degrees.
The measure of the elevation angle. And now what are you saying, Leanne? It's very close to 83. Now, the question would be, how much different is 83 from 84?
It's a degree difference.
But slope difference. So this is 50/5, right? On our 10/1, on this 84 degrees. Let's also write 50/5. the question is, let's leave this as approximately 50 feet up. At what denominator would this turn into 83 degrees? So it's got to be more than 5, right? Because this would have to go further out. This 5 would have to go further out. And that answer is actually, I'm not going to make us solve it. It's actually 6. 5 over 6 is the approximate. If that tower goes 1 foot further, right, it's going.
Oh.
So they have, I'm pretty sure there are like support cables on this now or whatever, but they have done a lot to try to make sure this won't happen. Like done some sub-support structure and stuff like that.
That'd be a special experience going on it and then having it fall.
Oh, you're not allowed up it anymore. Yeah, they've shut the tower down. Like it's not safe.
Why don't they just
I think it has settled. Like I think they followed it and they've got like really particular cameras on it and computer programs and stuff like that. And I think it has not moved like at all. For a while.
Because no one has gone on it.
Fix it?
Fix
What do you
it.
mean straighten it up? You want to straighten the leaning tower of Pisa. Then it would just be the Tower of Pisa and people would be like, meh. You know the real answer of why don't they fix it? Because now the fun thing to do is this.
But you don't.
Is, get pictures as if you were holding up the tower. That's why. Now to make sure we get you to lunch early, let's pack up. That's it for today. So the tower's safe for now.
There's no